Welcome everyone. I'm Dr. J.D. Armstrong. I'm the Maui Technology, Education, and Outreach Specialist here at the University of Hawaii Institute for Astronomy. One of the things I get to do is put together these public talks, and every now and then I will take over one of the public talks to give an explanation that I want to give. And that's what's going on today, is I'm going to discuss how a telescope works. So this is an explanation that I developed as part of an engineering class I gave over at the University of Hawaii Maui College. And hopefully, after this talk, you'll be able to explain a little bit about how a telescope works. So let's start off by first letting you know next public talk will be Friday, January 23rd, and that will be Guy Jett, who's been here many times before, always gives a great talk. So I'm going to start off with three simple rules of optics. First of all is that a beam of light travels in a straight line unless it's acted on by an optical force. So this is kind of a body in motion tends to stay in motion is my analogy that I'm hoping for here. But we can see that if we take, say, a laser, a pointer, and very carefully we can map out which direction that light goes. Okay? And so here's a nice picture of that. This is actually the laser ranging station up on the summit of Haleakala, and we see the beam of light coming out from the station and going up into the sky, and it is in a straight line. Okay? The second rule is reflection. So if we have a beam of light come into a surface that reflects it, say a mirror, then the angle that it comes into the surface, that it hits the surface at, is going to be equal to the angle that it leaves. This is the angle of incidence equals the angle of reflection. Okay? So this angle here, the angle that it strikes the mirror, is equal to the angle that it leaves the mirror. And the third simple law is Snell's law. This is, well, it gets into a little bit of trigonometry, and I know that every time I put a formula up, at least 3 people fall asleep. So let me just explain what it means. If you have a beam of light coming into a substance that is more optically dense, say from air into glass or water, from air into just about everything, the light travels slower. And so this side of the beam of light gets slowed down before this side of the beam of light. And so instead of traveling straight, it'll bend down a little bit. And this equation tells us how much it bends down. But the important thing is that we can bend light by having it go from one medium into another, like from air into glass or air into water. Okay? Couple of simple concepts that will make this this journey a little bit easier is that light generally goes outwards in all directions. So if we have a star here, the light goes in every different direction. It goes up, down, left, right, backwards, forwards, and every direction in between. Okay? And the other simple concept is the idea of a wave front. This is the surface that is perpendicular to the direction of travel of the light. Okay, that sounds complicated, but it's not so hard. If you look, this is the direction. The arrows are pointing towards me, towards the right hand of the screen. So the surface will be up and down in this case. The wave front will be up and down. Or in this circle, they're all going outwards, and so there's a circle. In the case of a star, the light is going out in all directions, so there's a circular surface. Okay? And this is another, further wavefront that's further out is also still can be a wavefront. It's just basically you look at the direction the light is traveling and you put a surface that's perpendicular to that direction so that the direction of light is pointing into or out of that surface. Okay? And as we get farther away from a source, the wavefront gets flatter and the rays get closer to parallel. So if you have a source here very close to the star, it's a very tight circle. As we get farther from the circle, the wavefront gets larger, the circle gets larger, and the same area of the wavefront will be closer and closer to flat. And the rays coming out will get closer and closer to parallel. So here they are spreading out there. By the time they get out here, they're even closer to parallel. And by the time the light from a star that's maybe 4 light years away for the closest star, 4.26 light years to Proxima Centauri, by the time the light gets all that distance, it's basically a flat wavefront and all the rays are parallel. Okay? If we get far enough away from the source, the wavefront basically is flat and the rays are parallel. So that's the case we're going to consider for astronomy, because we're using telescopes for astronomy. We don't know anything else that telescopes are used for, right? Okay, so let's discuss the simplest telescope. The simplest telescope is a pinhole. And this was actually used by the Vatican Observatory and other places. They have made pinhole telescopes. A pinhole telescope is, just imagine a screen with a single hole in it. Now, how does this work? Well, as all good astronomers in Hawaii can do, I've learned how to draw a stick figure tree. And so let's look at this stick figure tree. We've got the green leaves and the brown trunk. And over here, we're going to put a screen. So the light from, say, this point on the tree, this green light is coming out and going in all directions. And so it comes over here and it hits the screen and stops. It hits the aperture and stops. And notice that the light is going to be green because it came from a green source. Okay? Some of the light is going to come from this green spot and will come down here and will hit the block and will not make it to the screen, and so it gets stopped. But some of the light will actually go through the pinhole. Just this one ray of light will go through the pinhole. Anything further up gets blocked, anything further down gets blocked. And furthermore, any light from other places aren't going to end up at the same place on the screen. Therefore, all the light hitting the screen at this spot is green because it all came from that green spot. So let's do another thing. So we have a green spot from here. Sorry, I have to replay this. Okay, we've got a green spot from there. Now we have another spot over here that's also green, and it'll put a green spot there. We'll have a green spot or a brown spot from the trunk here. Maybe some other part of the trunk also we have to consider. So there'll be a brown spot there, and there, and there. And pretty soon we can map this out, and all of this is brown, all of this is green, and we get an image. We start to develop an image of the tree. And notice that it's upside down. It's a real image. It projects onto a screen, very much like this screen here. It's a real image that projects onto a screen, and notice that it's inverted. The leaves end up down here, and the trunk ends up here. And you can actually try this. If you take a window covering and put a small hole in it, and maybe the size of a penny, and then it should project an image onto the other side of your room. Okay? Really wanted to make the point that it's real and inverted. So that's why we had to flash that on there several times, I guess. So now let's consider the case of two stars. Now remember, stars are very far away, so all of the light is going to be parallel. Okay? This goes back to our two simple concepts. As we get far away from a source, the wave front gets flatter and the rays get closer to parallel. So the light coming from this blue star is actually much, much farther away. It's really out at infinity, and all this light is coming in parallel, and this one ray makes it through to the screen over here. But there's another star over here, a red star. We're just imagining. Okay, so we're talking about another a star over here. It also has parallel rays coming in, and this one is the only one that will make it through the pinhole. So it goes there, and that's where we get our image of that star. That's where the red light shows up. Okay. In this case, angle is converted into position. So the angle of these parallel rays coming through the pinhole is converted into a position of the stars. So if we imagine looking at a galaxy, each one of these little dots is infinitely far away, and so the light is coming in parallel from each little dot, but there's an angular separation between each point on the image. And so you can project this galaxy, this image of the galaxy, onto a screen using this pinhole approach. But the problem is that it's very faint. The farther we put the screen from the pinhole, the larger the image gets. This is a very important point. Just from simple geometry, the farther this separation is, then the larger this image gets. Okay, because the angle here is defined by the image that you're projecting from the object. Okay, so this angle is preserved, and you can move this screen back. As you move the screen back, it gets larger and larger and fainter and fainter. All right. So you have this engineering trade-off. The larger the pinhole, the more light we get, right? And that's a good thing. We want more light. We want bright images. But the detail, yes. A larger pinhole is like painting with a larger paintbrush. And so the spots of light coming through with the larger pinhole, oh, and there's, okay, everyone's keeping track of my typos? There's one, okay. Okay, so the larger the pinhole, the larger the paintbrush that we're painting with, it's more light but less detail. So there's a trade-off. Wouldn't it be great if we could have a really big pinhole and still have small detail? Still have the small brush that we're painting with. Okay, so we need to have a way to have a bigger opening and still put all of the light coming in at the same angle onto the same spot. Yes? So the idea that you present is to use multiple pinholes, right? But if you put a pinhole down here, then this image would be shifted down a little bit. And so that's a really good idea. And at one point I saw some sunglasses that were supposed to make your vision really good because it's just a pinhole. But it was a whole bunch of pinholes. And so it kind of didn't work. Yes? Do a bunch in a line? Well, yeah, I mean, whatever direction you're stretching out these pinholes, you've got a big brush in that direction. And so maybe you just have a slit, but in this direction, it's blurry. In this direction, you've got a lot of detail. Okay? And for those of you who know Fourier optics, yes, let's not get into the rest of what slits are used for in optics. We can show some spectra later. So the way to get a big opening and still bring the light into focus is to use a lens. So you remember that I said that glass can bend light, right? Okay. So what we do is we make a shape out of glass, and the shape is determined by what we want to do. And this is, hundreds of years old, but it's very well known. And here's what we want it to do. A line going through the center of the lens will keep going straight. Okay, so if it goes right through the center of the lens, it goes through as just like it was the pinhole. All right, so we can keep this in mind, that this is the ray that goes through the pinhole. All right, okay, the ray going through the middle of the lens goes straight through the lens. The parallel rays going through a lens come together at the same distance from the lens. And this is called the focal length. That distance is called the focal length. So if we have a star here, and remember stars are infinitely far away, so their light is parallel for all intents and purposes. You have light coming through. What's going to happen to this first blue line? Goes straight through. What's going to happen to these two? They're going to bend together, and they're going to come to a point at the distance from the lens, at one focal length from the lens. Okay, so you'll get an image of the star there, right? Okay, and if we have another star over here, we have the light coming there. What's going to happen to this middle ray? Is it going through the center of the lens? It's supposed to be going through the center of the lens. Okay, pretend it is. If my drawing is a little off, pretend it is. So this center line, what's going to happen to that? It's going to go straight through. These lines will bend, and they should all cross at this distance, right? Okay, this line, so it's going to show up right about here, correct? Okay, so there we go. This line goes through, this one gets bent, this one gets bent, and we get our image of the other star there. Yeah?
So if you look at one star through a glass, but if you look with it without glasses, it'll show up like those two over there.
Mm-hmm.
And if you look with glasses on, it'll show up like that.
Well, not so much with glasses. Some glasses are these convex lenses. So the question was, if you look at the star without glasses or with glasses, whether or not they'll show up like this over here. Okay, some glasses are convex like this, and those are in case you can't see when things that are very close up. But for people that wear glasses for distance, those are actually kind of the reverse of this shape. It's thin in the middle and thick on the edges. And that makes the light kind of go out like this, and then the person's eye can focus it. Okay? So, all right, and if we put a screen, so back to this, if we put a screen right here, then all the red light is coming together here, correct? And all the blue light is coming together there. So are we going to get a real image? Are we going to see an image on the screen? Yes. Okay. And so if we have this image way out there, we have the lens, okay, then we'll get a real image of whatever we're looking at, and it'll be inverted. Notice this is upside down, and we can put it on a screen and actually see it. This is an example of a real image. Okay? So here's the second simplest telescope, the human eye. Everyone is carrying around a simple telescope with them right now. In fact, two of them, your eyes. So at the front of our eyes, there's a lens, right? You guys have all heard this in science class. The front of your eyes there's a lens. And so that lens is going to form an image on the back of the eye, right? Okay, it's going to go through the lens and form an image on the back of the eye. Okay, and this is an actual image of the human retina. I got this from Wikipedia. I can't remember who took it, but this is a healthy human retina. So this is the screen that's on the back of the eye. And we project our image onto the retina. The lens from our eye actually projects a real image onto the retina. And if our retina were a screen, maybe we could look in somebody's eye and see an image of ourselves being projected on the back of their eye. Okay? So it's a real image that's being projected on the back of the eye. And so if you have, and then each one of these dots represents a cell in your eye that is sensitive to light. And so what happens in the back of our eye is this cell here measures how bright the light hitting it is. Okay? And this cell here measures how bright the light. And this cell here, all the different cells measure how bright the light is. And then we can put that together as a picture. Is that making sense? I'm going to use you guys kind of as my gauge. Does that make sense to you? Okay. Yeah? So you'll pass the quiz if I give you a quiz later on? Okay. All right, thank you. All right. So each point in the image, we measure how bright the light is at each point in the image of this real image that's projected onto a whole bunch of detectors. Okay? All right. So a refracting telescope, we can do the same thing. Instead of a retina back here, what do we use? Not a mirror, because you're not going to reflect it. What do we use to detect light in a telescope? Do you know? No, not glass. We're trying to detect the light. We're not trying to bend it or change it. Oh, what we have back here is, let's imagine, let's think of a bunch of photomultiplier tubes or a bunch of little detectors, a bunch of photoreceptors or photodiodes or whatever technology we want to do. And we put a bunch of them together in a small area and we measure the light at each point. Yes?
So like they have different like circular things that look at the photo and they see how bright it is using like a brightness scale.
That's correct. So the comment is, back here, they have a bunch of little photodetectors, and each photodetector measures how bright the light is in the image at that point in the image, and it records it and puts it on your computer. And then all of the different points put together make the picture. That's correct. And we call this wonderful device usually a CCD, or a CMOS. There are various technologies, and if you have a tablet with a camera or a cell phone with a camera or even just a digital camera, you own either a CCD or a CMOS. I think they're pretty much always CMOS. CCD stands for Charged Coupled Device. I don't know. I can explain the technology of it, but let's just take it on faith that it's an array, a whole bunch of points of little light detectors. Okay, that could be a whole nother talk. Okay? All right. So this is a refracting telescope. Now the problem with refracting telescopes, we want to make a bigger and bigger telescope, right? Because bigger telescopes mean more light. Does it mean a bigger image necessarily? No. If we want a bigger image, all we have to do is make smaller detectors and pack them in a little closer, and then just blow it up on the computer. So the main purpose of a telescope is what? To gather the light, to collect the light. Exactly. The main purpose of a telescope is to collect or gather light. All right. Now, if we imagine making a big lens, let's say I want a 2-meter lens. Okay, it's a disc of glass this big around, and I've got to hold that up by the edges. Does anyone see a problem with that engineering feat? Right, it's very difficult to get a really big lens and hold it by the edges. But so what we want to do is we want to find some way of making light come together without having a lens. This is the sort of technology that's used on the big modern telescopes. Instead of a lens, we use, well, smoke and mirrors, or actually just mirrors. Okay, so mirrors. We use what is called a reflecting telescope. And it's easiest to start off by talking about a less popular design, but conceptually easier to talk about, and that is an off-axis telescope. The reason these are less popular is that making the mirrors the right shape is more difficult, and until recent engineering advances, they were almost prohibitively difficult. Nowadays, we can make these. We make these all the time. And so this is a diagram of the Solar Sea telescope. This is one of the telescopes up on the summit of Haleakala. And Jeff Kuhn and some other people designed and built this telescope. Part of it was to prove this concept for the off-axis telescope design. And how many of you have heard about the solar telescope that's being built up there? Good. I hope most of you have heard about it. It has an off-axis design as well, and this was the telescope that was used to prove that concept. This was the telescope itself, in this case, was as much of the experiment as any of the science done on it. Okay, so let's look at what's called an off-axis telescope design first, and then we'll come back to the more normal on-axis design. So we have the image out here, okay, and the light comes out. We want a bowl-shaped mirror because a bowl-shaped mirror will bring the light together, correct? And so we want to do all of the things we did with a lens, but in a reflection. So the middle ray of light should go to some place, and then all the other rays of light should come together. All right? So this ray, this ray, this ray, this ray, they should all come together somewhere over here. Okay, all of those rays should come together as a point over there. So let's start off with this point. That line's going to go over here. And we have this place here, so we know what angle the mirror should be at this point. We know what angle the mirror needs to be at that point, that point. And so we have all the light come together. And remember that this is for parallel rays, and then when they're off a little bit in angle, it'll move off a little bit in the position. And so we'll get our image again. It'll be real, it'll be inverted, and there will actually be a real image that you project. And what do we project it onto on professional telescopes? A CCD. So by using the proper bowl shape on a mirror, we can do the same thing as with a lens. Is that making sense? Good. All right. And just for argument's sake, I can throw another mirror in here. Let's say that this time it's a flat mirror. Sometimes they're not, but let's just say it is. And that could just direct the image over there. Okay? Good.
This is all mathematics.
Yeah, this is all mathematics, but it has been tried. And in fact, for example, this is a mirror from a telescope. And if you go ahead and look at this mirror, you can possibly tell that it's a little bit curved. Yeah. Yeah, go ahead and pass that around. And thank you to Rob Rakowski for letting me borrow these. One of these days we will get these recoded for you. Okay. All right. Well, the biggest telescopes in the world generally are segmented mirrors. In other words, they're pieces of mirrors. So for example, the Keck Observatory is a segmented mirror. The 30-meter telescope that is being planned is a segmented mirror. There are several different pieces of mirrors, and they just put them together. So let's think about how we would do that.
30-meter mirror, is that across the diameter?
The diameter of the 30-meter telescope, the diameter will be 30 meters. The Keck telescope, which has already been built over on Mauna Kea, and it's been in operation for a number of years, that's 10 meters in diameter, so about 30 feet in diameter. Yes. Yes. Okay. So let's start off with our off-axis design. We have a little piece of a mirror here. We have a mirror there. It's curved. It puts an image down here. Now I can take another mirror and put it right next to it, and it will also form an image. Right? Haven't done any sleight of hand yet. Okay. Well, now what I'm going to do is I'm going to tip this up a little bit so that those two images overlap. Can I do that? Sure, why not? Okay. Now, is there going to be a hole in that image? The amateur astronomers are going, oh, I see what you just did there. Good, good. There's not a hole in that image because, well, there's no hole. It's just the image from this is lying on top of the image from this. Okay. So now we could add a third mirror down here, right? And put it over there. We could put a mirror up here and add it there. We put one here, put a whole bunch of pieces, add it, and just tweak them so that they're the right shape and pointed in the right direction, and all the images from all of these little pieces come together in the same place.
Is that a better image?
There is,
My question to you, I have one mirror that gives me an image.
mm-hmm.
You put two, do I get a better image, or is it improved?
So,
how is it improved?
So the question is, if you've got one mirror, you have an image. Now, if you have two mirrors, is that image improved? Well, you've got twice as much light, so you can see a fainter object with it. There is an effect that that shows up if you have a segmented mirror due to Fourier optics, due to the wave nature of light. You get some scattered light, you get some fringing, but if you're looking for faint objects, this is the way we have to go. We cannot make a 30-meter single piece of glass. It would just be impossible. So what we do is we have 31-meter pieces of glass across. So nearly 900 pieces of glass in this 30-meter telescope on a big, huge scaffolding that we then can point around at the sky. All right? So now that we've talked about off-axis design and segmented mirrors, let's go back to what this telescope right here is like. Okay, this is an on-axis design. So all we have is we've got a round mirror. Okay, there's a round mirror. The light comes in, bounces off the round mirror, goes up to a secondary mirror, and then comes through a hole in the back of the mirror. Now, we can think of it as this piece of the mirror puts the image here, and this piece of the mirror also puts the image there. Okay? So I'll get to your comment or question in just a sec. So one question is, whenever someone sees an on-axis design like this is, well, is there a hole in the image? What do you think? Is there a hole in the image? No. Good. Then I've tricked you into understanding that. All right. Yes, sir.
Well, when it bounces off the bent edges and it goes towards the actual picture, it looks. Didn't you say that it bounces off the mirrors at the exact same angle? It doesn't look like it over there.
Okay. The question is that the angles that it doesn't look like it bounces off of the correct angles. It's flawed artwork. It's not a flawed concept. You brought your imagination with you, right? Okay, so in your imagination, go ahead and fix the angles so that there he rolls his eyes up into his head. That's brilliant. Okay, so just pretend that the artwork is correct. By this time it was about 2:30 in the morning last night. Okay, yes.
Does that design mean that you have, it looks like you can put fewer mirrors, or it doesn't have the light gathering capability? Is that the difference?
Yes, so the question is, it looks like there's less light gathering capability. Yeah, and that's true, because the light where the secondary mirror is blocked. The light coming in here gets blocked by the secondary mirror, and then of course the shadow of that secondary mirror will fall on the hole in the primary telescope, or in the primary mirror. Okay? Yes, sir.
So in that diagram of the telescope, the picture comes out upside down over there. But then
Yes.
when you look through a regular telescope, why doesn't the picture come out upside down?
So the question is, in this diagram, the picture comes out upside down, and why is it that when you look through a regular telescope, the image does not come out upside down? Let's get you on a telescope tonight. They are upside down. Rob, am I lying to these guys? Okay. Now, binoculars are another thing. So when you use a pair of binoculars, these have been designed. I'd better put that down before I break something. So if you have a pair of binoculars, these are designed so the image is flipped back up. Okay? Yes, sir.
But then, like, when I got a telescope for, when I got one for my birthday, like, when I was really young,
Mm-hmm.
this telescope, when I looked through it, I looked at a tree and it wasn't upside down.
Okay, so the question was, this young man, when he got a telescope for his birthday a number of years ago, he looked at a tree and it wasn't upside down. Well, okay, we could put another element in there that can flip it up right side up. But really, already we're talking about something slightly different, right? We're talking about a telescope that we look through an eyepiece. Okay? So something like this. All right. Thank you for the lead-in. That was beautiful. Okay. Do you have a quick question? Okay. Okay. We'll save his questions to the end. Thank you. So let's talk about a telescope with an eyepiece. So let's have a lens in front that has a long focal length, and then a lens in back that has a short focal length. Okay? Is everyone comfortable with that? All right. So light coming in, it's going to come in and it's going to cross over at the focal length for this lens. And the center line, well, that's easy to go through both the lenses, because if they're centered, then that line will go through all the way through both lenses. Correct? Okay. Now the question is, what happens over here? You know, what happens after the image plane, the focal plane from the first lens? Well, the way light is if you go this way and it follows some path, going the other way, it'll follow the same path backwards. Okay, so we can think about what would happen to parallel lines of light coming in this way, going backwards through the system. They would come together right here. So what's this length here? That's the focal length of that lens. So we have, here's the focal point, the focal plane for that lens, and it's the focal plane for that lens.
How does the light go back?
We just are imagining the light going backwards. We could actually turn the telescope around and look in the wrong end, but that seems kind of to defeat the purpose.
For the light to get back to that focal point, there must be something to turn it around.
Well, it's not necessarily getting back to this focal point. So it comes in this way and then goes to this focal point. If we were to shine light in this lens from this side, it would come to a focus here. Okay? But really what's happening is the light is going from this focal plane this way through the lens. It's continuing on through the system.
That second lens then, if I got the focal point over there.
Well, because we want to look through the telescope. This is a telescope that we are going to put our eye up against. And so we want parallel lines again. We want parallel rays again.
So you don't really look at the focal point, you're looking at the
Yeah.
parallel.
Yeah. So that's exactly the point that I want to make is with this system, we go in through a focus, and then this lens makes the rays parallel again. Correct? All right. And so at this stage, if I were to put my eye right here, it would look like that star was infinitely far away. Correct? Correct? Because I've got parallel light coming into my eye. All right? And notice how spaced the lines are over here. They're a lot closer together over here. What does that mean about brightness? More contrast, more concentrated, more brightness. Yeah, exactly. Got like 4 people right here that gave me all the answers. Okay, so basically you're using all of this lens and squeezing the light down until it will fit in your eye. That will make the objects appear much brighter. Okay? All right, so the telescope intensifies the light. It doesn't really intensify the light, maybe that's a bad thing, but it gathers the light. It concentrates the light. Of course, there's another factor, which is magnification, and the magnification will cancel out the amount of increase in light, ironically. So, now this is for light coming in perpendicular to the lens. Now let's think about what happens as far as the size of the image. Okay? So we have light coming in at a little bit of a different angle. Okay? And to show you this, let me do this. So here's the light coming through. Here's our focal plane right here. And this ray really goes up this way. But we know that all the light comes together in lines to this point, correct? So now let's look at the line that goes through the center of the lens. Why do we want to look at the line going through the center of the lens?
Because then instead of that one, it'll come up more clear to your eyes.
Not quite.
It'll come actually to your eyes and like right here or something.
What is the rule for a ray of light going through the center of a lens? Goes through straight. So this is the easy one to think about, right? Because it goes through straight, right. So this one goes through straight. We know that here's the plane. we don't know where this one comes from, but this ray that goes through the center of the lens is going to go through straight, correct? Okay. Now, so the telescope, look at this. This is not very much of an angle. But coming out, it's a much bigger angle, correct? What does bigger angle mean as far as the image size on our eye? It's a bigger image, so we get magnification. Okay? So the telescope increases the angle of light entering by the ratio of the focal lengths. In other words, if the focal length of this lens is 2 meters and the focal length of this lens is 1 meter, it'll be 2 to 1. It'll increase it by 2. Yeah, the magnification will be 2. Very good.
So what you're saying is that's the way I want to look at the light. The previous, you had it right on.
Mm-hmm.
This one you're looking at it from an angle. So
Well,
I'd rather have my lens at that angle, the light coming in at an angle.
well, no, the reason that we're looking at the angle of the light coming in is because the angle of light coming into our eye determines how big the image, how big we see the image. Okay? Remember, angle gets converted into position on our image. Okay? And so this, by looking at the different angles, this angle is bigger than this one now. And so this means the image is going to be bigger and it's magnified. That's what I'm trying to convey here. Does that make sense or not quite? Not quite. Yeah, go ahead.
The previous slide, the angle came in, well, the one that, yeah, it came in like that. And,
Mm-hmm.
but it wasn't, the image is, when you don't have a diagram on it, but
Mm-hmm.
it's not as large as that second slide.
Right. So it's not as large as that second slide. Well, this is on axis. And all of these lines are parallel coming in. All of them are parallel coming out. Then we put our eye here, and our eye will bring those parallel lines, parallel rays together into a single point, into one single point of the image. So all we're doing is we're considering a single point in the image and that's very far away.
And the second slide, you had a bigger angle.
So at the second slide, I put an angle in here. Okay, so that's another point in the image. Okay? So it's a slightly different point in the image. So it comes in at a slightly different angle. Light is coming into the telescope at a slightly different angle.
So that second mirror, the second image here, could I tilt that mirror? If the light is coming straight in, can I just tilt that second mirror there to bend the light to make it bigger?
No, it's not. The question is, could we tilt the lens to make the image bigger? It's not really that you're tilting the lens to make the image bigger. We're considering, okay, think of this as the blue star over there, okay? This blue star is way over there, okay? And this red star is way over there. So on my image plane, here's the position of the red star, correct? And here's the position of the blue star. Okay? All right. Now, we come through the second lens, and this is just, we're only showing the light from the blue star. We're not showing all the light. All the light is coming through it, but we're only considering the light from that one point in the image. And the idea is to consider how big a distance between the blue star and the red star are going to be when they get back onto your retina. And the way to determine how far apart they're going to be on your retina is to consider the angles that they're going into your eye. I know it's a very difficult concept. Does that sort of make sense? Yeah. Think about it for a little bit, and then afterwards, if you want, we can sit down with a piece of paper and a pencil and draw this out. Okay? Yes?
I added 2 more lenses into my telescope.
Mm-hmm.
Would it increase the magnification of the image that's coming through?
So the question is, if we add 2 more lenses into the telescope, would it increase the magnification? So say that again louder. If it's smaller than the one before it. In other words, yes or no, it depends on the focal length of the lens. There's what's called a 4F system, which is 2 lenses with the same focal length. And so imagine this being the same focal length of this. And then we separate them by twice the focal length. You'll form the image right here. And then it'll go back out, and the parallel lines leaving will be the same spacing as the parallel lines coming in. The angles will all be preserved. And so all it does is it flips things upside down and relays the light. So it really depends on, you know, the magnification you get out of it will depend on the focal lengths of the additional lenses. We do manipulate the light like that by adding extra lenses to change the size of the focal length or how big the beam is for what we refer to as the beam, which is all the light for the image we want. We do put extra lenses in some of these systems in order to control that. Okay? Yes, sir.
Wait, so like stay on the slide.
Mm-hmm.
So you know how you said that when the star shoots like in all these directions, it eventually comes to it shoots like that and eventually becomes parallel.
Mm-hmm.
Well, if it shoots like that, doesn't it eventually have to cross each other at the end of the last?
Oh, so the light coming in is crossing like this? Yeah.
Doesn't it eventually have to do it on the other side?
Not if they're parallel again. Yeah, these lines are parallel again. Okay, so maybe out at infinity they'll cross again. So a very, very, very large distance. They might cross again, or maybe they're just slightly diverging, and so they'll keep on spreading out. It depends on exactly where this is, because the position of the lens will change between coming together versus spreading out. Okay? All right? Okay. So the telescope increases the angle of the entering light, of the light leaving by a factor of the ratio of the focal lengths, and that translates into a magnification. Okay, a larger angle results in a larger final image on the retina, and as this young man said, if the primary lens, if the objective lens has a focal length of 2 meters, and this one has a focal length of 1 meter, the magnification will be a factor of 2. The image will be twice as big. Okay? And I think that that's good enough to torture your brains for the evening. Thank you very much. All right, do we have any questions or? Yes.
Okay, so I buy myself a telescope, or let's say it's a pair of binoculars, and
Mhm.
it's 20 power. What
Yes.
does that actually mean?
So if the question is, if I buy a pair of binoculars and they say 20 power, what does that mean? It means that for things that are here on Earth, let's say I'm looking at a tree, and let's say I'm 20 miles away from the tree. Okay? And I look through this 20 power telescope or binoculars, it'll look like I'm only 1 mile away from the tree. okay, the image will appear to be 20 times larger, or it'll be or it'll look like you're 1/20th of the distance away. So the ratio of the focal lengths would be 20:1. Exactly. This one's Akamai. We got to talk to him some more. Okay. Also, I think, before I forget, I think that some of you might be here because you want advice on how to buy a telescope. Is anyone in that kind of position? Okay, now turn around and look at the three gentlemen in the back row right there. Those are very good people to talk to about buying a telescope. Yeah. Okay, those are Dr. John Pye is on the left. He teaches astronomy over at Maui College, and all three of them are members of the Haleakala Amateur Astronomers Club. For those of you in the virtual audience, if you want help buying a telescope, look up your local amateur astronomy club, give them a call, drop them an email. They probably will love to hear from you. Go out with them a couple of times, and before you actually buy the telescope, ask for some advice. Pardon, Stefan? Or Safan is another excellent. Okay, all four of the people in the back row would be excellent at helping you choose a telescope to purchase. Yes.
In a segmented telescope, is each mirror a concave mirror, or do they form one big concave mirror together?
Okay. The question is, in a segmented mirror, is each segment a concave mirror, or do they form a big concave mirror altogether? Both. They are. Each segment is a concave mirror. It's a curved mirror, and then you put these pieces together, and it would form a continuous bowl, a continuous curve. Okay.
What would a 30-meter telescope do that a 10-meter telescope can't then?
So the question is, what would a 30-meter telescope do that a 10-meter telescope cannot? A 30-meter telescope will see something 1/9 as bright as what can be seen by a 10-meter telescope. It will gather 9 times the light, correct. Okay. All right, and then you're next.
Can you tell us something about the reflector in the off-axis telescope? That has to be a special reflector.
It's the question is to tell you something about the reflector in the off-axis telescope. Let's go back and take a look at that. So the primary mirror, maybe I should have just missed it, didn't I? Yes, that is cheating. Thank you. There we go. Slideshow. All right. So basically, this mirror down here, the shape of it is slightly off compared to, you have a very specific shape here that brings the light together the way we want. But if you look at this part of the mirror, at the left half of this mirror, we'll say, okay, it's different from the center of the mirror. You can't just rotate it over to the center of the mirror. So basically, this mirror, it's almost like, now that's a half-meter diameter mirror. And it's almost like they made roughly a 2-meter mirror and then drilled out the shape, the half meter from over here. Okay, that's not really how they do it, but the shape is the same as if they had. There's a tilt to the curvature and an asymmetry to the curvature that if it's not there, we have what's called coma, or actually astigmatism. John, correct me if I'm. Yeah, it would be astigmatism. Yes, and some of you have correction for astigmatism in your lenses, in your eye, in the lenses of your eyeglasses. Basically, what that is when the light comes to a focus in this direction at a different distance than in this direction. And so you put a cylindrical lens in to get them to come together at the same direction. Okay? And so when you use an on-axis mirror off-axis, you actually introduce astigmatism. You have to adjust for that in the curvature of the mirror. Okay? And you're good. Okay. Yes?
Well, I was also thinking that the arrays where they have multiple telescopes,
Mm-hmm.
I mean, it looks like they're all pointing in the same direction. Are they essentially just, and then they're just combined computerized
Mm-hmm.
as if it was one with multiple mirrors? Is that what they're doing?
Yeah. Okay, so the question is, yeah, like the VLA. Okay, so the question is, she's thinking about these arrays of telescopes, like the Very Large Array, in which you have these multiple dishes and they're all pointed in the same direction. And how are they combined? Are they combined, put together as a single, like they're a single telescope, and then how do they do that? Is that correct?
Yeah, are you essentially, instead of doing it in one telescope, you're doing it in multiple dishes? Is that what
Yeah.
you're doing?
Yes, so the Very Large Array is a radio telescope.
The radio,
Okay,
Never mind.
but no, that's perfectly valid, because radio is a different color of light, a different frequency of light. Okay, but the frequency of radio waves is low enough that they can combine the signal without actually overlapping the images. And so they actually are using all of those radio dishes as a single telescope, as a single multi-segmented telescope. One of the projects that I'm aware of is a sparse aperture, or a sparsely, it's basically about 3 or 4 small mirrors like this that bring the light together, and from each of these 4 segments. And then there's a lot of space in between. There was a proposal to add some outriggers to the Keck Observatory, which were small, I believe they were about 1 meter telescopes, and then you combined all the light together to form an interferometer, and it would have made it possible to see resolution much larger, much better spatial resolution. There is a limit to how small you can get your spots, the size of your spot, depending on the color of light you're looking at and the diameter of the telescope. Okay.
So with the Keck outliers, does that mean you'd get more spatial resolution, but you wouldn't get any more light, so you'd need more sensitive?
So, yeah, the question is, well, with the Keck outriggers, does that mean you don't get any more light, but you do get better spatial resolution? With the Keck outriggers, if they had done that project, you would only have gotten a little bit extra light, but you would have gotten considerably more spatial resolution. Now, if you're looking for, say, an asteroid, which is going to still be a dot of light, that resolution actually helps you because it brings all the light down into a smaller spot and it would look brighter. Depends on what you're looking at for astronomical telescopes. We have a question online? Are there any other off-axis telescopes in existence running today? I believe there are. I know there was one that they tried to build in Chile that I believe was not very successful. But I think that there are. And I know that there are some amateur astronomer telescopes. Some amateurs are beginning to say, oh yeah, off-axis telescopes are the way to go. The reason is, has everyone in here seen an image from the Hubble telescope? And the stars aren't just dots, they have this kind of cross to them. Okay? That's because you need some way of holding up that secondary mirror, and so you have a cross in there. And it's actually this part of the spider, which is the structure that holds up the secondary mirror, that creates the spike in this direction. And this part of the spider creates the spike in this direction. Okay? That's the real advantage to having an off-axis telescope, is you reduce that scattered light. You don't have something in the field of view that will actually mess up the image in some non-geometric optics ways. So I didn't get really into how it messes them up, but having objects in the field of view, not only do you lose light, but you create problems on the image that have to be understood or hopefully fixed and removed. Okay? Good? Yes. That's great, having a question from the in-worlds. Thank you, guys. All right. Any other questions? All right. Oh, yes, one more.
I'd like to make a comment. James and I went to the Bishop Museum Center for Astronomy,
Mm-hmm.
and what you're saying is exactly the images that they had projected on their iMacs.
Oh, thank you.
Very much.
All right. The comment was that they just had been to the Bishop Museum, and what I was presenting here was basically the same thing that they were presenting over there. So, okay, well, good to have that confirmation. Do we have another question from InWorlds? Oh, okay. Hello. Yes. So the comment from InWorlds was that someone watching is from the Bishop Museum and said to say hello to everyone. Thank you. Aloha.